Hey guys, today we'll be going over covectors and the tensor product. This video is going to be a bit more abstract and less intuitive than the other videos. And you'll see that in a moment. But with enough patience and practice, you'll get it just fine. Okay, so we all know what covectors are. That's a prerequisite for this whole series. Know what covectors are. Covectors are they're like a stack of lines. So here we have a field, okay? We have a scalar field. And here we have a covector. Here we have a covector. So a covector is like a stack of lines. And we can see that we can transform a scalar field to a covector. And this covector is a stack of lines. And the value throughout this entire line is 0. The value throughout this entire line is 1, and so on. They're pretty abstract, but they're pretty useful as well, as we'll see in a future video. And we can have a vector. When a covector acts on the vector, it's just that vector lying on the covector, and then counting the number of lines the vector pierces the covector lines. So here we have a vector v. The vector pierces three lines. Okay, so the covector acting on the vector would equal 3. That's a brief rundown of covectors, and it turns out that we can transform any scalar field into a covector. And that's where the beauty of covectors lies. And we can do integration with these covectors, and we'll do that in a future video. So this is a scalar field F, okay? Scalar field F, and dF is a covector field. In this case, it's just one covector, but it turns out we can have a field of covectors. So, yeah, you have a scalar field F. You can transform it into a covector by taking dF, and we can expand the covector dF in the multivariable chain rule. And here we can immediately see our basis. The dx and dy would be our covector basis, and these terms over here would be the covector components. And we can actually write covectors. We can write df as a row vector in that form. Partial f over partial x, partial f over partial y, given some basis dci. Okay? And a covector isn't a row vector. It's not even a vector. A covector can be represented as a row vector in that form. Oh, it's not really being represented as a row vector. It's just in that horizontal matrix 2x1 matrix form. So, yeah, covectors are different than vectors in the sense how they actually transform in a different way. And I promise I will not be talking about any transformations in this video other than that, because our last few videos have just been transformation after transformation, and it gets a little repetitive. So we're not going to deal with any transformations in this video, but covectors are different from vectors in the sense that they are a stack of lines on a space, pretty much. Okay. So yeah, you can probably find out how they transform by just doing the same things we've been doing in a different video. Just transform these two over here. Okay, So, as I've said, covectors can act on vectors. That's a major property of a covector. So here we have a covector acting on a vector. Actually, this should be df. Ooh, actually, never mind. Let's go here. Here we have a covector df acting on a vector, well, a vector field, really. dr over d lambda. And that will equal this over here. And let's prove that. Let's prove it. Okay, before we prove it, we have to talk about basis vectors. How is the covector basis related to the vector basis? Because we can't make covectors act on vectors if we're dealing with different bases in different bases. You can't multiply things that are represented in different coordinate systems, right? So how can we get the covector basis from the vector basis? How can we do that? Well, the covector basis, so pretty much let dcj be a covector basis. It is compatible with partial r over partial ci if partial r over ci times cj, the dot product, equals the Carter delta. That's how we uh that's how we find the covector basis in the same coordinate system. So when I said we can't compare different bases, that was kind of wrong. I mean different coordinate systems, because in nature the covector basis is different from the vector basis. It's just that they're in the same coordinate system when when you multiply them, you get the Carter delta. That's when they're represented in the same coordinate system. Okay, so using that we can prove this over here. What this is basically saying is that if we have a covector, df equals partial f over partial x, partial f over partial y, and then dr over d lambda equals dx over d lambda, dy over d lambda. It's basically saying that when we multiply these two together, when we multiply df by this vector, when we multiply them, that it's going to equal this times this plus this times this. That's what it's saying. It's going to equal partial f over partial x dx over d lambda plus partial f over partial y dy over d lambda. Now this may seem obvious. No kidding, Sherlock. Of course it's that. But we've seen in the past that the dot product between two things isn't always the sum of the product of the components of those two things. Like the dot product between two vectors, v and w, isn't always the summation viwi. Is it always that? It's in general, it's viwj times gij, where GHA is the metric tensor component. Okay, so how do we know that this dot product is just this times this? How do we know that there isn't some hidden metric tensor lying out there, some ghost tensor? Like, how do we know that? Well, we now actually prove that right now. Okay, so 1 second. Okay, so to prove that, we have to expand df and dr over d lambda. Df is just partial f over partial x. Well, let's actually expand it in the abstract form. df cj and then dcj, then times dci over d lambda partial r over ci. And that should equal this. Well, we're gonna see if it actually equals that. We're gonna see. So first we just rearrange some of the terms. Just rearrange some terms over here. And now we have dcj dotted with partial r over ci. Now remember, we just said that if dcj is the covector basis, it is compatible with this, like they're in the same coordinate system, if partial r over partial ci dotted with, well, we can make arrows here? I did not know that. That's pretty cool, actually. Sorry. So if partial r over partial ci dotted with dcj, AC coordinate is the coordinate delta. So we're assuming that we're dealing with it with the same coordinate system here, and which means that this dot product has to be the Kronecker delta. In this case, yeah, delta ij. We have partial f over partial cj, dci over d lambda. We can then just change j to I, and then we have this over here, which, surprise, is the exact, is the same thing. Yeah, and this will go to 1. So that's the same thing that we have right here. So we've just proved that. Now let's also prove a unique property of covectors, that dci multiplied by dr over d lambda is dci over d lambda, or in the English word, the basis, the ith coordinate of a covector basis times a vector is going to be the ith coordinates of that vector. Let's prove that real quick. First, let's just erase all of this. Okay, so we prove that by expanding them, obviously, in the abstract form. Let's make the cj times dci over d lambda partial r over ci. And that equals, we're gonna see what it equals. So first we just move these two, put them together. Cj dci over d lambda times dcj dotted with partial r over partial ci. And remember, if we recall correctly, this has to equal the Kronecker delta, since we're dealing with the same coordinate system. Let's change j to I. J to i's. Partial f over c dci over d lambda. That's what we get. Okay. I just made a stupid mistake. I made a pretty dumb mistake. Sorry, that was wrong. See, we expanded DCI as DF, DCI, DCI. But that's not what DCI is. That's just DF. That's what that is. My bad. This, we don't expand it into anything. We have to expand this, though. We expand that into DCI over D lambda, partial R over partial CI. We move this to the front. Then we take this dot product. And as we've seen, surprise, it is the Kronecker delta. Sorry, let's make this J. Okay. Sorry, make this I, make this a J, make this a J, yeah. Change the indices to make the summation work properly. This would be a J, this would be a J. This should be a J as well. Okay, yeah. And that gives us the Kronecker delta. Change our J to I, and we get DCI over D lambda. There's not even a J term here, which is the same thing as here. So it means that the dot product between the covector and the vector is just the sum of the product of the components of the respective elements. So that 5 times fast. Last part of this video, I'm going to go over the tensor product. This is a very abstract thing, and it might take a while to get. But the tensor product between a vector and a covector is denoted as a cross. It's an operation that takes the vector in the matrix form, and the covector in the matrix form, and creates a matrix. We just like multiply this and this to get this term, this and this to get this term, and so on. So the tensor product between a vector and a covector is when you write them in their respective matrix forms, and then create a 2x2 matrix from that, or a bigger matrix depending on the dimensions of your space. Okay, and what we get is that a linear map is just the tensor product between a covector and a vector to multiply by the linear map components. And I haven't talked about linear maps in this series because that's just in linear algebra. But you may have not have heard it explicitly called a linear map. You may have heard it called a linear transformation. They're pretty much the same thing, but not exactly. But the linear map is a matrix that you multiply, but that you multiply on a vector to make a new vector from linear algebra. Or in other words, L acting on V gives you W, a new vector. And you can actually find the linear map transformation from the formula for L. I'll let that be an exercise for the watcher. A bit of a twist to the exercise for the reader. Joke. And it turns out that the metric tensor is just the components times the tensor product between dx and dy, the covector bases. Sorry, this should be sorry, my bad. Actually, ooh, we made a pretty bad mistake. Pretty bad mistake here. Actually, no. No, no, no. We did not make a mistake. We did not make a mistake. Did we? Did we make a mistake? I'm trying to think if I made a mistake right here. Okay, yeah. We made a small, very small mistake. We have a summation here. This should be CI. And this should be CJ. My bad. This should be the basis vector itself. My bad. Oops. And then yeah. But this still stands. That still stands. However, take the dot product between a basis vector, partial R over CJ, divided with a covector basis, or the dual basis that some might call it. You do the same thing, except that you have to write this as like some. I know it makes no sense. I'm trying to explain this in the best way. It's a pretty abstract concept, but you have to write your basis vectors as an actual matrix, which might sound pretty weird, and it really is pretty weird. But you'd have to write it out as a matrix. Like, you have to define your basis vectors as some number in a matrix, pretty much, okay? So, yeah, your linear maps equal this if this basis is orthonormal, okay? If you're dealing with an orthonormal basis, Cartesian basis, whatever you want to call it, an orthonormal coordinate system, as your linear map formula. And this should also be orthonormal for your metric tensor. So yeah, that's pretty much it. I know, like, I was pretty hand wavy out of that section, but that's the whole gist of it. And you may have noticed that the actual math itself, like the symbols that we've been using, have pretty much been the same since like video 1. And it may make you think, oh, is tensor calculus just these symbols all over again? Like, and it really is. Tensor calculus, we're gonna deal with the same symbols over and over again until we hit differential geometry. Then we're gonna get some new symbols like the nabla symbol and the del symbol. It's gonna be pretty cool. Oh, and the Christoffel symbols as well, gamma. So yeah, but as of now, the actual symbols that we've been using, it pretty much looks the same. So yeah, that's the whole gist of it. Have a great day.